The property relations for mixtures. In Chapter 30, our consideration of mixture was limited to ideal gases. There was no need at that point for further expansion of subject. We now continue this subject with a view toward developing the property relation for mixture. This subject will be particularly relevant to our consideration of chemical equilibrium in Chapter 16. For a mixture, any extensive property X is a function of temperature and pressure of mixture and the number of moles of each component. So we can write X is a function of temperature, pressure, NA and NB. Therefore, dx T and P equals to NB, and DNA multiplied to DNA plus round X on round NB at T and P constant and also NA constant DNB. Since at constant temperature and pressure an extensive property is directly proportional to the mass, can be integrated to give X, T and P XA NA plus XB NB, where XA on X on round NA TPNB and XB on X on NB TPNB. Here X bar is defined as partial molar properties. X bar partial molar property for a component in a mixture. It is particularly important to note that the partial molar property is defined under condition of constant temperature and pressure. The partial molar property is a particular significance when a mixture undergoes a chemical reaction defined in under conditions of constant temperature and pressure. The partial molar property is particularly significant when a mixture undergoes a chemical reaction. Significance when a mixture undergoes a chemical reaction. Suppose a mixture consists of components A and B and a chemical reaction takes place. Suppose a mixture consists of components A and B and a chemical reaction takes place so that the number of moles of A is changed by DNA. Change in number of mole A and DNV change in number of mole of B. It's because A and B, the temperature and the pressure remain constant. T and P constant. What is the change in internal energy of mixture? So we can write the change of the U, T and P for a mixture at P and A pressure constant. U, B, D and B, the change of the G, where U bar A and U bar B are the partial molar internal energy of A and B. U bar A and U bar B partial molar internal energy. Equations. This equation suggests that the partial molar internal energy of each component can also be defined as the internal energy of the component as it exists in the mixture. In the section 14.3, we consider the number of property relation for system of a fixed mass, such as the relation for du equals to TdS minus PdV. In this equation, temperature is intensive property of potential function associated with entropy, and pressure is the intensive property associated with volume. Suppose we have a chemical reaction such as described in the previous paragraph. How would we modify this property relation for this situation? Intuitively, we may write the equation as du for a chemical reaction du ds minus pdv plus mu b dnb, where mu a is the intensive property or potential function associated with Na, mu a is the intensive property or potential function associated with Na, and mu b for Nb. Intensive properties potential function associated with Nb. Chemical potential. This potential function is called the chemical potential. To derive an expression for the chemical potential, consider the equation here. And conclude that may be reasonable to write an expression for U as U equals to F S V N A N B. Du on U on Ron S V N A N B ds plus the second term where is V round U or round V S N A and N B constant multiply to dV. If you write another color round U on round NA at SVNB constant plus DNA round V on round B SVN A DNB. Since the expression round U on round S round U on round S at VNANB T and round U on round V S and A and B thus du equals to TdS minus PdV plus round U on round NA SVNB DNA plus round U on round NB SVNA DNB. On comparing these equations for the chemical reaction equation for DU in the previous page, this equation, we find that the chemical potential can be defined by the relation chemical potential mu A equals to and mu B round U on round NB SVNA. We can also relate the chemical potential to the partial molar Gibbs function. We proceed as follows. Chemical potential to the partial molar Gibbs function. Potential to the partial molar Gibbs function molar Gibbs function. U plus PV minus TS du plus PdV plus VdP minus TdS plus S dt. Substituting to the previous equation, dg minus S dt v dp plus mu na and mu b dnb. And now g equals to a function of t, p, na and nb with a derivative for dg. According to previous relation, we can obtain dg from t, p, n, a, and b dt rho g on rho p t, n, a, nb dp plus rho g on rho na tp nb tpna dna plus the rest term rho g on rho nb tpna constant tpna constant multiply dnb. The mathematical differential case of dg should be equals to minus s dt, previous relation, v dp plus rho g rho na tpnb dna rho g on rho nb tpna dnb. When this equation is compared with each other, we can find the mu b and mu b and mu a as these two relations. So for gives equation mu b rho g on rho na tpnb and mu b nb tpna. Because partial molar properties are defined at constant temperature and pressure, the quantities expressed here are the partial molar Gibbs function for the two components. Partial molar Gibbs function for chemical potential coefficients. And expressed as G bar A and G bar B. Although mu can also be defined in terms of other properties, such the equation 16.9, this expression is not the partial molar internal energy, since the pressure and temperature are not constants in the partial derivative. The partial molar Gibbs function is an extremely important property in thermodynamic analysis of chemical reactions. For at constant temperature and pressure, it is a measure of chemical potential or deriving from that tends to make a chemical reaction take place. Pseudo pure substance model for real gas mixture is the next section.